Good morning, mathematicians, and welcome back. Today we're going to do some cohomology of profinite groups, moving forward in our saga. Morning, mathematicians. I might change the lighting. But let's get ourselves set up here first with chat. Oh. Yeah, I was watching tires on a pirating site. I mean, oh crap. Should I have that on camera? I mean, I paid for it. Let's see, is the lighting better with this? No, it's not really any better. What about noob finite groups? Yeah, well, I think those are just ordinary finite groups for us. So we've already studied them. Mind you, I guess finite groups are profinite too, actually. But I mean, you know, pros could compete in noob tournaments. They just elect not to. But noobs couldn't compete in pro tournaments, so... yeah, I stand by noob finite groups being just finite groups. Okay. So we've got direct limits. Okay, we're just recalling some basic definitions for limits of groups. Yada yada. But... now, I guess we want to consider G modules for which the map is continuous when M is endowed with the discrete topology equivalently to being continuous. The stabilizer of every element is open, and M is the union of the fixed point sets as H runs through the open subgroups. Cool. This is definitely, also very related to representations of p-adic groups. We take these same sort of definitions. Although, the p-adic groups themselves aren't profinite, necessarily. That I deal with, but we take these same definitions. Discrete G modules are still abelian with enough injectives. Okay, I guess I'll just believe it. By taking injective resolutions, just as before. And so we define the groups using continuous cocycles. So if phi is a continuous R cochain, oh, then the image of phi is compact? What? Because GR is compact? Oh, right. Profinite is compact. Is that true? That's true, right? I think that's true. Yeah, that's like a basic fact about profinite groups, right? He probably said that early in the document. Every profinite is compact and totally disconnected. Yeah, and in fact, isn't that a characterization? Aren't all compact totally disconnected groups profinite? Am I crazy to be thinking that's true? So the image is compact and discrete, and so it's finite. And so it's actually contained in MH0 for some open normal subgroup. Wait, why normal? Probably just some argument from the system of... because the profinite is the limit... over the normal subgroups. Okay, sure. I'll take that as a vague argument. Might be missing some adjectives, but the characterization sounds familiar. Yeah. Let's just look it up. Profinite if and only if compact and totally disconnected. Totally disconnected from reality, am I right, baby? So AI says yes. Oh, they tosses in the word Hausdorff. Oh, well, I was already on the Wikipedia page. I probably just looked here. Yeah. Yeah. This says compact and totally disconnected topological group, but does topological group secretly mean Hausdorff as well? Anywho. So the inverse image of each point is open, and so contains a translate of HMR. What dost thou meanest? Now I'm a little confused. Hello, good morning. Now I'm a little confused. For some, what is H of M supposed to be? Is the group right translated by M? I guess so, because I mean, just based off of this being an intersection, so this must be a set. I'm guessing it's the set where we've translated by M on the right. And then this is R copies. But then why are we saying a translate of this thing? Gosh, that's confusing. Okay. Okay. This is again an open subgroup of G, and gamma factors through this. Define H this way, and then phi arises by inflation from an R cocycle. Okay, so I think the point we're going for here... Oh, H is just the normal subgroup. It depends on M. I see. Okay, that makes sense. Thanks, Arad. Right, and then, okay, I think I see where we're going with this. Well, we're going... Well, now I can see this down here. But this also... Okay, we're looking at the technical details, but this is a very believable thing, right? Like, you would want the cohomology of a profinite group to be a limit of the cohomology of the quotients. So that makes sense. Let me grab some water.
My water bottle.
Okay, I hope you guys were able to thoroughly entertain yourselves by reading on screen while I was searching for my water bottle. That was punishment. My water bottle splashed me. That was punishment from the gods of math for leaving you guys alone and unsupervised for too long. Okay, anyways, this is a very believable theorem. Because passage to direct limit commutes, kernels, co-kernels, we obtain the following proposition. So the inflation maps from each of these quotients realize the continuous cohomology as a direct limit of these groups as H runs through the open normal subgroups. Sweet. Cool. I guess we could apply that right away then to compute, now that we have these theorems about cyclic groups, we could apply this to compute some cohomology of the p-adics, or z hat. Z hat being the Galois group of finite field. Explicitly, the statement means that each element yeah, okay. For every profinite group and discrete G module, HRGM is torsion. And this, right, just follows from, well, G mod H is finite? Right, yeah. Most of the theory continues to hold. For closed subgroups, we get all of these properties. Okay, this is bold, so it's important. We got to memorize it. In the future, all cohomology groups will be defined using continuous cochains. Okay, I guess we'll just remember that. In practice, this will mean that G is an infinite or profinite group. Doesn't that apply just as well to the finite groups? Just slap a discrete topology on everything. And it matters that we take continuous cochains or G is finite, in which case it doesn't. Oh, I see. Yeah. Yeah. How are we doing, gang? Chat is very slow today. Is it because I'm is it because we're really slogging through the details now in this cohomology of group saga? Perhaps it's a sign I should be switching to something new and more interesting. At some point, I do want to do spectral sequences, but we're on the verge of getting to some actual number theory here, so. Okay. So let G be profinite. Suppose that M is discrete. It's because I'm making you feel guilty for not writing the blog. Oh, well, that's true. But obviously I'm not making you feel guilty enough because you're here watching the stream instead of working on your blog. Or maybe you've got the stream open in another tab or another window or another device, and you're working on your blog simultaneously. That would be the best of all worlds because I want to read your blog and I want you to be here in chat to join us. The Gaga saga. Yeah, that could be good. That could be good if we could do the Gaga saga. That would be good. Yes. Very mildly guilty. Okay, I'm gonna have to. I don't know. I'm gonna have to pressure you more. We need more people in chat to pressure Rod into writing more blog posts. Okay. So, if G's profinite, M is a discrete G module, and if M itself is a limit, then we also have limits here. Wow, everything's just limits of limits. Because G is compact, M is discrete, the image of a cochain is finite. Since MI form a directed system of submodules, there should be and M is the union of these. Every finite subset is contained in some I, right? Wait, in one single I, is that true? Yeah. Oh, because I guess it's a directed system. And then it follows that we have this limit of cochains, and then by this lemma, okay, we just argued that it preserves the cochains. Ooh, 4 experts. That's not me. That's not us. So we're not allowed to read this. But you know what? We're going to do it anyways. Yeah, no one can stop us. But they will have video evidence that we did it. Consider the category of all G modules and the category of discrete modules. It's a full subcategory. Moreover, there is a functor to the union of what? Of taking fixed points over all the things? Okay, I see. Right, gotcha. And clearly it's an adjunction. So the inclusion functor is exact, but doesn't preserve injectives. Hence, these aren't equal in general. On the other hand, the other functor preserves injectives, but it's only left exact. So this thing has enough injectives. Ooh, however, there's a spectral sequence, ... I mean, okay, Gaga Saga does have a great name. However, we are at some point going to jump off and go do the spectral sequences mini saga. In the 1930s, Herwick showed that the homology group of an aspherical space... Okay, we're just not going to define that, I guess. What is an aspherical space? A spherical space. Something, none of the homotopy groups are isomorphic to the groups of spheres or something. Oh, okay. Just the higher homotopy groups vanish. Okay. That was easy. Oh, he said that. See? Look, I made the mistake I've criticized other students of. I just didn't read the next sentence. Thus, we can think of the homology groups of the space as being the homology groups of the group corresponding to it. It was only in the mid-1940s that all of our favorite friends gave purely algebraic definitions of homology and cohomology of a group. It was then found that H1 coincided with crossed homomorphisms. That's interesting. That's interesting that that was the order of discovery. There's this folklore result that the first 13 stable homotopy groups of spheres can be computed from the Serre spectral sequence, but the 14th is impossible. Wow, interesting. Huh. Yeah, I'm curious as to what goes wrong at 14. I'm guessing, yeah, just some random algebra and number theory come together in a weird way that makes some, I don't know, calculation suddenly intractable. Our proof of Tate's theorem follows Tate's original proof. At that time, there was no published account of the Tate groups. So he provided his theorem only for r greater than 0, but ended with an enigmatic promise to extend the result to negative r and recover the Artin map. The construction of Tate cohomology groups was then published by Cartan and Eilenberg. Huh. Speaking of Tate, as you guys probably know, I have an interview now with Professor Joe Silverman of elliptic curve fame. So you should go check it out. A good source for the material in the first three sections was this. A Tia wall, as Arad had suggested. Yeah. Okay. Well, that might do it for today, right? We're at about half an hour. Ooh, look at Milne coming out here with these nice colorful diagrams. That's nice. So boom, we're done. We finished cohomology of groups. Now it's time to get into some number theory. So I guess tomorrow this is where we'll start with local class field theory, cohomology of unramified extensions. So looking forward to it. I guess I will see